Somewhere out there, past the last whisper of the solar wind, past the final trace of the sun's magnetic influence, past the place where our home star's breath becomes indistinguishable from the galaxy's own sigh, a machine built almost 50 years ago is still doing something it was never meant to do. It is listening, not for signals we sent, not for echoes of planets long since past, but for something far quieter, far older, and far stranger. The low, steady hum of the space between the stars themselves. And what it has heard changes everything we thought we knew about the medium that surrounds our entire solar system. Voyager 1 is now more than 24 billion kilometers from Earth. That number is so large, it becomes meaningless without context. It is roughly 164 times the distance from Earth to the Sun. A radio signal traveling at the speed of light takes over 22.5 hours to go from mission control to the spacecraft, and another 22.5 hours for any reply to come back. When NASA engineers want to send a command, they wait nearly 2 days just to learn whether it worked. And yet, from that unimaginable distance, Voyager 1 is sending back data that no human instrument has ever collected before. Data that contains a persistent faint hum, a plasma wave oscillation oscillating at around 3 kilohertz, ringing through the ionized gas of interstellar space like a bell that never stops vibrating. This is not background noise from the cosmos as we normally understand it. It is not the cosmic microwave background radiation left over from the Big Bang. That's a different frequency entirely, a faint glow in the microwave part of the spectrum. It is not the hiss of galactic cosmic rays hitting a detector. Those are high-energy particles, not waves. It is not even a signal from a distant star or a pulsar. What Voyager 1 has detected is a continuous, low-frequency fluctuation in the density of the interstellar plasma itself. Think of it as the ambient soundtrack of the galaxy's gas, the way a humming transformer or a distant waterfall creates a background tone in a room. Except this transformer is the entire local galactic environment, and the room is the space between the Sun and the next star. Before Voyager 1 crossed the heliopause in August 2012, scientists had only indirect models of what that plasma density should be. They could estimate it from observations of distant stars, from the way radio waves from pulsars are scattered as they travel through the interstellar medium, from the properties of cosmic rays that reach Earth. But all of those methods are like trying to describe the sound of a forest by listening to the echoes off a mountain miles away. Voyager 1 is the first and only instrument we have ever placed inside that forest. And the moment it arrived, it began telling us that the forest sounds very different than we imagined. The hum itself was not discovered immediately. After crossing the heliopause, Voyager 1's plasma wave subsystem continued to operate, but the plasma density it measured seemed to vary in ways that were hard to explain. Occasionally, the spacecraft would detect a burst of plasma oscillations triggered by a shock wave from the Sun, even though the Sun's influence was supposed to be negligible out there. Those bursts would briefly excite the surrounding plasma, and scientists could use the frequency of the resulting oscillations to calculate the local electron density. But between those bursts, the signal would fall silent. Then, over years of careful observation, a pattern emerged. Even when there were no solar shocks, even when the plasma seemed quiet, there was a faint, continuous signal. It was not loud. It was barely above the noise floor of the instrument, but it was persistent. It was present in data from 2017, from 2018, from 2019, from every year since the crossing, and it was always around 3 kilohertz. That frequency corresponds to a specific plasma density. By analyzing the hum, scientists at the University of Iowa and Cornell University, led by doctoral researcher Stella Koch-Ocker, were able to directly measure the electron density of the interstellar medium around Voyager 1. The result? About 0.1 electrons per cubic centimeter. That number is remarkably consistent with some theoretical predictions, but it is also far more precise and more detailed than anything models could offer. And because the hum is continuous, it allows scientists to track how that density changes over time and over distance as Voyager 1 drifts farther into the unknown. Now, you might have heard some confusion about the Oort cloud in relation to Voyager 1's signal. Let me clear that up right now. The Oort cloud is a vast hypothetical sphere of icy bodies that is thought to surround the solar system at distances between a few thousand and perhaps 100,000 astronomical units from the Sun. Voyager 1 is currently at about 164 astronomical units. It has not even begun to approach the inner edge of the Oort cloud, which is generally placed somewhere around 1,000 to 2,000 astronomical units. Even if the Oort cloud were full of plasma, which it is not, because it is mostly solid chunks of ice and rock, the hum Voyager is hearing is coming from the plasma immediately surrounding the spacecraft, not from some distant source. The instrument is measuring the density of the gas that Voyager is actually flying through. There is no interference from the Oort cloud. The Oort cloud, in fact, is so far away that Voyager will not reach it for another 300 years at its current speed. The hum is local. It is immediate. It is the voice of the interstellar medium right here, right now, as we drift through it. So why is this hum so important? Because it gives us a new tool to study the environment that our entire solar system swims through. The interstellar medium is not empty. It is a dynamic, magnetized, ionized gas that is shaped by supernova explosions, stellar winds, and the overall structure of the Milky Way. The density of that gas determines how the heliosphere, the Sun's protective bubble, is compressed or expanded. It influences how cosmic rays penetrate into the solar system, which in turn affects everything from spacecraft electronics to cloud formation on Earth. By understanding the interstellar medium, we understand the larger context in which our planet exists. And until Voyager 1 crossed the boundary, we were guessing. Now we are measuring. The hum also reveals something more subtle. Because it is continuous, it means that the interstellar plasma is not uniformly calm. There are tiny fluctuations, small variations in density that travel as waves. These waves might be generated by distant processes, perhaps by the turbulence of the galaxy itself, perhaps by the passage of Voyager through the medium, perhaps by some unknown source. The fact that we can detect them at all is a testament to the sensitivity of an instrument designed in the 1970s, built to listen to the radio emissions of Jupiter and Saturn, and now repurposed as the first interstellar marine. Every year the spacecraft survives, we get more data, more details, more evidence of a universe that is far from silent. Let me take a step back and describe exactly how Voyager got here, because the story of its journey is essential to understanding why this hum feels like a miracle. The spacecraft launched in September 1977, riding a rare alignment of the outer planets that occurs only once every 175 years. It was meant to fly by Jupiter and Saturn, take pictures, measure magnetic fields, and then fade into obscurity. That alone would have been a historic mission. But Voyager 1 did not fade. After its Saturn encounter in 1980, mission planners made a fateful decision to get a close look at Titan, Saturn's largest moon. They chose a trajectory that would fling Voyager 1 out of the plane of the solar system forever. That single choice ended its planetary tour and sent it on a one-way trip into the unknown. For the next 3 decades, Voyager 1 continued to operate, hurtling outward at about 17 kilometers per second, while NASA gradually shut down non-essential instruments to conserve the fading power from its plutonium-based radioisotope thermoelectric generators. In 2012, scientists realized that Voyager 1 had crossed the heliopause, the boundary where the sun's solar wind is no longer strong enough to push back against the interstellar wind. The crossing was far sharper than anyone expected. Over just a couple of days, the count of solar wind particles dropped to nearly 0. Cosmic rays from the galaxy surged, and the magnetic field direction shifted. It was like passing through an invisible wall. Since then, Voyager 1 has been in interstellar space, a region that only existed in theory until that moment. And then came the hum. It was not a single dramatic event. It was a slow realization that the data from the plasma wave instrument contained a signal that never went away. Scientists published their findings in 2021, and the world paid attention. But the hum did not stop being detected. It continued through the years and continues still, as long as the instrument is operational. Now, here is a detail that often gets overlooked. Voyager 1 is not the only spacecraft to have heard this hum. Its twin, Voyager 2, crossed the heliopause in 2018 at a different location and also detected a similar continuous plasma wave signal. That confirmation is crucial. It tells us that the hum is not a local fluke, not something unique to Voyager 1's particular path. It is a genuine property of the interstellar medium, at least in the region near our solar system. The 2 Voyagers are now the first and only probes to have directly sampled the plasma density from 2 different points in the local galactic neighborhood. The data sets complement each other, showing that the hum varies slightly with location, but is fundamentally the same phenomenon, the background resonance of ionized gas between the stars. The fact that we still receive this data is almost absurd. Voyager 1's radio transmitter puts out about 23 watts of power. That is roughly the same as a refrigerator light bulb. By the time that signal reaches Earth, 24 billion kilometers away, it is so faint that it is measured in femtowatts, quadrillionths of a watt. To capture it, NASA uses the Deep Space Network, a collection of giant radio dishes, each up to 70 meters in diameter, tuned precisely to the frequency of Voyager's carrier wave. The signal is literally billions of times weaker than the background noise of the universe. But we can still pull it out, decode it, and extract the humming data that tells us about invisible plasma waves. That feat of engineering becomes even more incredible when you consider that Voyager 1 suffered a major failure in late 2023. The spacecraft suddenly started sending back gibberish, corrupted telemetry that made no sense. The issue was traced to a memory failure in the flight data system, one of the core computers that packages all scientific data before transmission. At 22.5 light-hours away, there was no possibility of a hardware swap or a physical repair. Engineers had to diagnose the problem remotely using only the limited diagnostics available from that distance. They determined that the only solution was to rewrite a portion of the software that had been written in the 1970s, using a programming language that is effectively ancient hieroglyphics to modern coders. They simulated the new code on Earth, uploaded it, and waited. 2 days later, Voyager 1 sent back a clean, valid signal. The spacecraft was alive again. Against all odds, a machine that was never built to be fixed from interstellar space was fixed, and it is still out there, listening. That is the context in which the hum exists. This is not a passive measurement from a comfortable distance. This is the product of decades of survival, of constant power management, of engineers coaxing every drop of energy from decaying generators, of an entire network of antennas on Earth straining to hear a whisper. Every bit of hum data is a victory over entropy. And yet, there remains a profound mystery. We do not know what generates the hum. The leading hypothesis is that it arises from the interaction of Voyager itself with the interstellar plasma, perhaps through the spacecraft's own electric fields or its motion through the gas. But alternative explanations exist. It could be a natural plasma wave mode called thermal noise, which occurs in any ionized gas. It could be a sign of turbulence in the interstellar medium that we have never observed directly before. Some researchers have even speculated that it might be related to the propagation of low-frequency radio waves from distant astronomical sources. The truth is, we are still learning. Voyager 1 is teaching us not just about the interstellar medium, but about how to interpret the signals an instrument makes while immersed in that medium. One of the most common misunderstandings is to think that this hum is somehow the sound of the galaxy, in the way we understand sound on Earth. It is not. There is no air in space. Sound waves require a material medium to compress and rarefy. And even though the interstellar plasma is a medium, it is extremely tenuous. The frequencies we measure correspond to oscillations in electron density, not pressure waves that would be audible if a human could be there. But the analogy is useful. It helps us imagine that the universe is not silent. It is full of vibrations, resonances, and waves of many kinds, all moving through the ionized gas that fills most of the cosmos. Voyager 1 is like a microphone dropped into that ocean, and the hum is the background rhythm of the ocean itself. Let me clarify another point that often causes confusion. Whether this hum is consistent with the cosmic microwave background. The CMB is a uniform radiation field at about 2.7 Kelvin, with a peak frequency in the microwave range around 160 GHz. Voyager's hum is at 3 GHz, which is radio frequency, not microwave. They are completely different phenomena. The CMB was emitted when the universe was only 380,000 years old. The hum is produced by the local plasma around us today. There is no relationship. The only thing they share is that both are omnipresent in their respective domains. Now, let's talk about the future. Voyager 1's power is expected to decline to the point where it can no longer operate any instruments around 2025 to 2030. The plasma wave subsystem will be one of the last to shut down, but eventually the spacecraft will fall silent. The hum will stop being transmitted to Earth, but the spacecraft itself will continue moving outward, carrying the golden record, that iconic message in a bottle containing sounds, images, and greetings from Earth. It will drift through the Oort cloud in about 300 years, then through the wider galaxy for millions of years, long after human civilization has changed beyond recognition. It will be humanity's first artifact to cross into the realm of the stars. And even after it stops speaking, the hum that it measured will remain in our databases, a permanent record of what the place between the stars sounded like when we finally arrived there. This is what makes Voyager 1's hum so haunting. It is not a discovery that will change technology or medicine or daily life. It is a discovery about where we live. We inhabit a solar system that is embedded in a larger environment, one that is dynamic, structured, and full of subtle activity. The hum is a reminder that the universe is not dead. It vibrates, it resonates, and we, through a fluke of engineering and a legacy of curiosity, have been able to place our ear against that vibration and listen. For some people, that might seem trivial, a 3 kHz tone in the middle of nowhere. But consider this. Every previous civilization looked up at the stars and saw only points of light. They could guess what lay between them, but they could never go there. We have gone there, not in person, but through a machine we built. And that machine is telling us what we whispered before it left. The interstellar medium is not just empty space. It is a real place with real properties, and we are beginning to map it from the inside. There is also a philosophical dimension that is hard to ignore. Voyager 1 is listening to something that no human has ever heard before. But in a sense, it is also listening to something that has always been there, waiting. For billions of years before Earth existed, the interstellar plasma hummed with these oscillations. After Earth is gone, it will continue. The hum is part of the natural order of the galaxy. We are latecomers, only now gaining the ability to notice it. And yet, in that noticing, there is a profound act of connection. The hum is not a message from aliens or a sign of intelligence. It is more basic than that. It is the voice of the raw material from which stars and planets and eventually life itself are made. The interstellar medium contains the debris of supernovae, the seeds of new solar systems, the chemical elements that make up our bodies. When we listen to the hum, we are listening to the background radiation of our own origins. That is why this story matters so much. Voyager 1 is a symbol of what we can achieve when we combine science, engineering, and a willingness to take risks. It was never supposed to be an interstellar probe. It was a planetary mission that got lucky. But that luck allowed us to do the impossible, to touch the space between the stars with our instruments. The hum is the proof of that touch. It is the evidence that humanity, for all its flaws, is capable of reaching beyond itself and learning something entirely new about the universe. Let me be very specific about the spacecraft and its location. We are talking about Voyager 1, launched in 1977. It is currently in interstellar space, beyond the heliopause, at a distance of roughly 164 astronomical units from the Sun. As of 2025, it is moving in the direction of the constellation Ophiuchus, heading toward a star called Gliese 445 in about 40,000 years. The hum is coming from the plasma through which Voyager 1 is traveling right now, not from any distant source. The Oort cloud is far beyond its current position, and no interference from that cloud has been observed or is expected for centuries. The hum is purely a product of the local interstellar medium. Now, I want you to imagine the scene, not with a telescope or a diagram, but with the mind's eye. Voyager 1 is a small spacecraft, about the size of a subcompact car, with a dish antenna pointing toward Earth. Its golden record is bolted to its side. Its power source is slowly dying. Around it, there is no starlight to speak of. The sun is just a bright star, not a warm disk. The darkness is absolute. The temperature is near absolute zero, and yet, in that void, there is a subtle oscillation, a rhythmic push and pull of electric fields and charged particles. That is what the plasma wave instrument detects. That is the hum. When I think about that, the machine, the distance, the signal, I feel a kind of awe that is hard to express in words. We are so used to thinking of space as silent and empty. But it isn't. It is filled with this quiet, steady sound, if only we know how to listen. And we do know, because we built a listener. And that listener is still out there, drifting, humming along with the universe. So the next time you look up at the night sky, remember that one of our own is out there, not just looking back, but listening. And what it hears is something no human has ever heard before. The voice of the galaxy itself, speaking in a language of plasma waves, telling us that we are not alone in the sense that counts. We are immersed in a living, vibrating cosmos. Voyager 1 may one day fall silent, but the hum it discovered will remain as a permanent testament that for a brief moment in history, a fragile machine from a small planet sailed into the great unknown and heard the music of the spheres. And that music will echo in the data long after the last watt of power is gone. But this music, this hum, is more than just a scientific curiosity. It is a tool, a diagnostic probe of the interstellar medium that we have only just learned to read. The plasma wave instrument on Voyager 1 was designed primarily to detect electron density along the spacecraft's path, not to act as a long-term monitor of background oscillations. Yet, because the hum is persistent and measurable year after year, scientists can now track how the density of the interstellar plasma changes as Voyager drifts farther from the heliopause. That is a monumental shift. Before Voyager, we could only infer interstellar plasma density from models based on radio observations of distant pulsars or the absorption lines in starlight. Those methods gave us average values over huge volumes of space. Voyager gives us point measurements, real-time, local, precise. And the hum is the key to those measurements. Every time the plasma wave instrument records a new peak in the frequency of the hum, it corresponds to a change in electron density. Scientists have noticed that the density has been slowly increasing since the crossing in 2012. That is not random. It tells us about the structure of the local interstellar cloud, the vast, tenuous region of gas and dust that our solar system is currently plowing through. Voyager 1 is like a buoy bobbing in a cosmic current, and the hum is the sound of the water pressing against it. We are mapping the texture of that current in a way no one ever imagined possible. And here is the part that makes this even more astonishing. The Voyager spacecraft are not optimized for this mission. They were designed for planetary flybys, not for interstellar sampling. The plasma wave instrument, for instance, has antennas that are only 10 meters long. Modern instruments would be far more sensitive with longer booms and better shielding. Yet despite these limitations, Voyager 1 is performing science that no later mission is currently equipped to replicate. There are proposals for a dedicated interstellar probe, something with modern sensors, a more powerful radio, and a longer operational life. But that mission is still decades away from launch, if it ever gets funded. Meanwhile, Voyager 1 is already there, already sending back data, already teaching us about the fabric of the galaxy. It is the imperfect pioneer, stumbling through the unknown and reporting back in a language of faint electronic whispers. Think about what that means for the future of interstellar exploration. If we ever send a dedicated interstellar mission, it will be able to refine the measurements Voyager 1 made. It will have spectrometers, magnetometers, and plasma wave detectors that are orders of magnitude better, but it will be standing on the shoulders of this 1970s workhorse. The hum Voyager 1 hears now is the baseline. It is the first draft of our map of interstellar space. Future scientists will look back at this data with the same reverence we look at Galileo's sketches of Jupiter's moons, clumsy, incomplete, but revolutionary. And let's not forget that Voyager 2, though it crossed the heliopause 6 years later, is also listening. Its hum is not identical. The density at its crossing point was slightly different, and the plasma frequency varied. That tells us that the interstellar medium is not perfectly homogeneous. There are gradients, patches, perhaps even ripples or waves that propagate through the material between stars. By comparing the two Voyager data streams, scientists can begin to reconstruct the three-dimensional structure of the local interstellar medium. It is like having two microphones in an enormous concert hall. You can start to triangulate where the sound originates. But unlike a concert hall, the sound is not coming from a single source. The hum is everywhere, and it is produced by the medium itself. That means we are not just hearing one note, we are hearing the entire hall resonating. One of the most profound implications of the hum is that it demonstrates the interstellar medium is not quiescent. It is dynamic. The hum shows that plasma waves are constantly being generated, perhaps by the relative motion of the solar system through the interstellar cloud, perhaps by the turbulence left behind by ancient supernovae, perhaps by magnetic reconnection events in the distant galaxy. The frequency and amplitude of the hum vary on timescales of weeks to years. That indicates real, active processes. The space between stars is not a peaceful vacuum. It is a turbulent sea of charged particles, magnetic fields, and low-frequency waves. We live inside a bubble that is sailing through that sea, and Voyager 1 has finally stuck its hand over the side to feel the water. Now, I want to address the question that inevitably arises. Could the hum be a sign of something artificial? Some corners of the internet have speculated that the persistent signal might be a transmission from an alien civilization, or perhaps a beacon. Let me be absolutely clear. The hum is not artificial. It is a natural physical phenomenon. There is no modulation, no pattern, no information content that would indicate a message. It is noise in the same way that the thermal noise in a radio receiver is noise. But it is a very specific type of noise, one that carries information about the medium it travels through. The idea that it might be artificial comes from a misunderstanding of the data. People hear the word signal and imagine something deliberate. But in physics, a signal is simply a measurable change in a field. The hum is a signal of plasma density, not a signal from a sender. It is the voice of the universe, not the whisper of an intelligence. Still, there is a poetic truth in that misunderstanding. The hum is a kind of message, not from aliens, but from the cosmos itself. It tells us that we are not isolated. The interstellar medium connects us to the rest of the galaxy. The carbon in our bodies was once part of that medium, forged in stars and expelled into the void. The hum is the sound of that ancient material moving around us. It is the echo of stellar life cycles, of the formation of solar systems, of the slow dance of galaxies. When we listen to the hum, we are listening to the origins of everything. And there is another layer to this. The hum is not static. As Voyager 1 drifts outward, the plasma environment changes. The heliosphere is not a perfect sphere. It is shaped like a comet, with a long tail behind it as the sun moves through the galaxy. Voyager 1 exited through the nose, so to speak, while Voyager 2 exited through the side. The data from both show different baseline densities and different hum characteristics. That means the interstellar medium is not only variable in space, but also in direction relative to the sun's motion. Future missions that go in different directions, perhaps out of the galactic plane or toward the galactic center, will encounter entirely different hums. The Voyagers are like the first two buckets dropped into an ocean that covers the entire galaxy. We have only tasted two tiny drops. The urgency of this mission cannot be overstated. Voyager 1's power supply is fading. By the time you finish reading this script, it may have already shut down one of its remaining instruments. The plasma wave subsystem is expected to operate until roughly 2025, perhaps a little longer if engineers can squeeze out more efficiency. After that, the hum will go silent. The data we have already received will remain, but no new measurements will come in. That is why every day of operation is precious. The spacecraft is a living artifact, and its death is approaching. The hum it hears now is a farewell song, a final report from the edge of the unknown. But the legacy of the hum extends beyond Voyager. It has inspired new research into interstellar plasma physics. Scientists are now reanalyzing data from other missions, like New Horizons, which is still inside the heliosphere, to see if similar low-frequency oscillations can be detected in the solar wind. Some researchers have proposed building a dedicated network of small spacecraft to map the interstellar medium in 3 dimensions, using the hum as a diagnostic. The Voyager data has proven that such a measurement is possible and valuable. It has opened a new field of observational astronomy, interstellar seismology, if you will, using plasma waves to probe the structure of the local galactic environment. There is a lesson here about human curiosity. When Voyager 1 was launched, no one thought about the hum. The instrument was included for reasons that had nothing to do with interstellar space. It was meant to study the plasma waves around Jupiter and Saturn. The fact that it is now being used to measure the density of the local interstellar medium is a testament to the versatility of good science instruments and the creativity of the scientists who operate them. It is also a reminder that the most profound discoveries often come from unexpected places. We set out to explore planets, and we ended up hearing the galaxy. As I write this, Voyager 1 is 24 billion kilometers away. That number is so large it loses meaning. Let me try to frame it differently. Light travels 300,000 kilometers per second. At the distance of Voyager 1, it takes 22 hours and 30 minutes for a signal to reach Earth. That means, when you read this script, the data it is based on, the answer is forever. In the vast, silent cathedral of space, a small, silent traveler is writing a story that will outlast us all. This is Voyager 1, and the question of how far it can travel has a simple, staggering answer. It will never truly stop. It will drift among the stars for eons, a permanent fixture in the cosmos long after the Earth from which it came has been erased. To understand this, we must not just measure in miles or kilometers, but in millennia. We must chart a course not just through space, but through deep, unfathomable time. Today, Voyager 1 is over 15 billion miles from Earth. A signal from it, traveling at the speed of light, takes more than 22 hours to reach us. It is the most distant human-made object in existence, a title it will almost certainly hold forever. It moves at a relentless 38,000 miles per hour. But this is just the opening sentence of an epic that spans cosmic eras. The immediate future is one of quiet, graceful decline. Voyager is dying, not from violence, but from cold, patient starvation. Its heart is 3 spheres of plutonium-238. As this radioactive material decays, it produces heat, which is converted into the precious few watts of electricity that power the spacecraft's brain and voice. But physics is inexorable. The plutonium has a half-life of 87.7 years. Every year, NASA loses about 4 watts of power. The engineers have performed a decades-long triage, switching off heaters, shutting down instruments one by one, conserving every joule of energy for the core systems that keep the antenna pointed at Earth. The mathematics are unforgiving. Sometime around 2025, the power will dip below the threshold needed to operate any of its remaining science instruments. The mission of discovery will end. Then, between 2030 and 2036, the last critical watt will fade. The temperature inside will plummet to near absolute zero. The transmitter will fall silent. On Earth, the giant radio ears of the Deep Space Network will listen intently one day and hear only the faint hiss of the universe. That will be the last whisper. After that, Voyager 1 transitions from a spacecraft to a relic, a ghost ship carrying a message, sailing into eternity. And here is the first great misconception to correct. Many believe that when Voyager's power dies, its journey is over. Nothing could be further from the truth. That moment is merely the end of its conversation with us. Its physical voyage is less than 1% complete. Others believe it has already left the solar system. This, too, is a matter of perspective. In 2012, Voyager 1 crossed a monumental threshold, the heliopause. This is the boundary where the outward pressure of the solar wind, a stream of charged particles blowing from the sun, meets the inward pressure of the interstellar medium, the thin gas and dust that fills the space between the stars. Crossing this boundary made it an interstellar traveler. But it did not leave the solar system. The true domain of our sun is defined by gravity, not wind. And gravitationally, our system is enclosed by a vast, spherical shell of icy debris called the Oort cloud. This is the source of our long-period comets, a frozen repository of primordial material from the solar system's birth. The inner edge of this cloud is believed to begin roughly 2,000 times farther from the Sun than Earth is. Its outer edge may extend 100,000 times that distance, or even farther. Traveling at its incredible speed, when will Voyager 1 reach this frontier? Not for another 300 years. It will spend 3 centuries drifting through the quiet, near-perfect vacuum before it even enters the Oort cloud. And to completely pass through it, that will take approximately 30,000 years. Let that time scale sink in. When Voyager 1 finally exits the gravitational grasp of our Sun and becomes truly adrift in the galactic tide, human civilization will be 300 centuries older. All of recorded history fits into a fraction of that time. Our languages, our nations, our very species may be unrecognizable. Yet, the trajectory calculated by engineers in 1977 will still be playing out with immutable precision. What is the environment like on this journey? For the craft itself, it is a state of near-perfect preservation. Space is an exquisite museum. There is no oxygen to cause rust, no moisture to enable corrosion, no weather to cause erosion. The primary threat is a random impact from a micrometeorite, but space is so empty and Voyager's cross-section so small that the probability of a catastrophic strike over the next million years is vanishingly low. It will fly on, intact, a fossil in a vacuum-sealed display case. Its first notable encounter after leaving the Oort cloud will occur in about 40,000 years. It will pass within 1.6 light-years of a small, dim red dwarf star known as Gliese 445 in the constellation Camelopardalis. This is not a close approach by cosmic standards. It's still over 100,000 times the distance from Earth to the Sun. It will be completely unaffected by the star's gravity, sailing past like a ship glimpsing a distant lighthouse. By this point, 40 millennia have passed. The probe is an ancient artifact from a civilization that may itself be ancient history. The milestones continue on a scale that bends the mind. In roughly 296,000 years, Voyager 1 will pass within about 4.3 light-years of Sirius, the brightest star in our night sky. Again, it is a distant, silent passage. On Earth, in that time, continents will have shifted. Ice ages will have come and gone dozens of times. Mountain ranges will have risen and been worn flat. The entire tapestry of life may have been rewoven. And yet this machine, built with 1970s technology, follows its preordained path. Now, accelerate the clock further, into the millions of years. At the 1 million year mark, Voyager will be about 88 trillion miles from its launch point. It is now a true galactic wanderer, drifting through the Orion arm of the Milky Way. It may pass within a few light-years of various anonymous red dwarf stars. Structurally, it is likely still intact. The aluminum of its structure, the gold plating on its famous record, the silicon of its chips, all are stable in the void. The golden record, a time capsule of sounds and images from Earth, is still technically playable, though there is nothing for light years in any direction that could play it. By 10 million years, the distance stretches toward a quadrillion miles. Here, we must introduce a new complexity. Nothing in the galaxy is static. Our Sun, along with every star Voyager passes, is orbiting the center of the Milky Way. The Sun completes one galactic orbit every 250 million years. So Voyager's path, while straight from its own perspective, becomes a complex, weaving spiral when viewed from the galaxy's core. It is like a single car driving in a straight line on a vast, spinning roundabout where all the other cars are also moving. Its trajectory relative to the Sun and other stars is constantly, slowly curling. Jump now to timescales where stars themselves are born and die. 1 billion years from now, Voyager has traveled quadrillions of miles. In this time frame, the galaxy has changed. Many of the bright stars we see today have exhausted their fuel, ending as white dwarfs, neutron stars, or in supernova explosions. New stars have ignited from stellar nurseries. Entire stellar generations have turned over. Voyager itself is now older than most of the stars it glides past. And what of its creator, the Sun? In about 5 billion years, our Sun will begin its death throes. It will swell into a red giant, likely engulfing Mercury, Venus, and possibly Earth. It will then shed its outer layers and collapse into a fading Earth-sized ember called a white dwarf. This cataclysm will be the final end for any earthly remains. But Voyager 1 will be oblivious. By that time, it will be tens of quadrillions of miles away. It will receive no increased light, feel no gravitational shift. It will not witness the death of its star. The Earth it knew will have been gone for billions of years. But the probe, carrying a record of that world, continues its endless migration. The cosmos itself has a life cycle. Current models suggest that in trillions of years, the universe will enter a degenerate era. Star formation will have ceased. The remaining lights will be the cooling corpses of stars, white dwarfs and neutron stars. Galaxies will have evaporated as their stars drift apart in an ever-accelerating, expanding universe. The cosmos will grow dark and cold. Even in this dying universe, Voyager could, in theory, persist. Over timescales so vast, they are written with exponents, 10, 30 years and beyond. Even the atomic nuclei in its structure may decay via quantum tunneling, or, by sheer statistical chance over these incomprehensible eons, its path could be bent by a chance gravitational encounter, sending it into a dead star or a black hole. But these are speculations on timescales that make the current age of the universe seem like a blink. So, to return to the original question with the full weight of this timeline, how far can Voyager 1 travel? The answer is not a number. It is a duration, forever. It will never coast to a stop. There is no friction in the vacuum of interstellar space to slow it down. No force, save the impossibly weak and distant tug of stars it never approaches closely, acts upon it. Its velocity is a permanent testament to the explosive energy of its 1977 launch and the gravitational slingshots of Jupiter and Saturn. The distances become meaningless. They simply accumulate infinitely. In 40,000 years, it passes a star. In 300,000, another. In millions of years, it wanders the galactic suburbs. In billions, it outlives its sun. In trillions, it drifts through a darkening cosmos. This transforms Voyager from a probe into something else entirely. It is a monument, a tombstone for humanity, not carved in stone but in trajectory and velocity. It is our most enduring artifact. On Earth, wind, water, and tectonic shifts will erase all our cities and monuments within a few 100,000 years. The Earth itself will be consumed, but Voyager, in its silent, deep freeze exile, will endure. The golden record it carries is not just a message for some hypothetical alien finder. It is a message to the future itself, cast into the cosmic ocean with no expectation of retrieval. It is proof that we were here, that we wondered, that we reached out. The final frontier for Voyager is not a place in space. It is a point in time beyond our ability to comprehend, where our species, our planet, and even our star are just faint memories in the history of the galaxy. Its journey is a lesson in humility and ambition. We built something so fragile yet so resilient that its echo will travel the galaxy long after our own voices have faded into silence. It is, in the most literal sense, our eternal voyage. But to truly comprehend the scale of this forever, we must zoom in from the cosmic to the microscopic, to the very engineering that allows this forever to be possible. Voyager's immortality is not an accident. It is the direct result of deliberate, foresighted choices made by engineers working with slide rules and paper schematics in the 1970s. Every contingency they planned for, every redundancy they built, was a bet placed on a future they would never see. And now, that bet is paying dividends in deep time. Consider the power system. The 3 radioisotope thermoelectric generators, RTGs, are marvels of passive engineering. They have no moving parts. The natural decay of plutonium-238 produces heat, and thermocouples convert that heat directly into electricity. It is a slow, inexorable process tied to the half-life of the material. This is why the decline is so predictable, allowing for a decades-long managed retreat of systems. Engineers didn't just build a power source, they built a countdown clock with a known rhythm, enabling them to meticulously plan the end of the mission's active life. The spacecraft's vitality is literally tied to nuclear physics, a clock that ticks for centuries. Or consider the fault protection. The spacecraft's computer systems are antiques, with less memory than a modern digital wristwatch. Yet they are robust, radiation-hardened, and possess a layered self-awareness. The now famous incident in 2022, where the Attitude and Articulation Control Subsystem, AACS, began sending garbled telemetry, is a perfect case study. For months, the spacecraft was effectively speaking in gibberish about its own orientation, yet it never entered safe mode. Why? Because its other systems confirmed it was still pointing its antenna correctly. The signal strength on Earth was unwavering. The spacecraft itself had enough innate intelligence to recognize that while one sensor's report was nonsense, the overall mission, pointing the antenna, was still being accomplished. It prioritized function over form, continuing to send pristine scientific data from its other instruments even as it babbled incoherently about itself. The fix, when it came, was a simple remote command to switch to a backup data routing system. A problem 15 billion miles away was diagnosed and solved by humans who could only send commands at the speed of light and wait 45 hours for a reply. This is not just engineering. It is a form of deep space medicine, practiced across a gulf so vast it defies human intuition. This resilience extends to the very structure. Voyager was built to survive the asteroid belt, a region once feared to be a chaotic shooting gallery. It was built to handle the intense radiation belts of Jupiter. Its components were tested to extremes that seemed absurd at the time. Now, those same qualities defended against the quiet, cold hostility of interstellar space. The primary enemy is not impact, but entropy, the gentle, universe-wide decay of ordered energy into disordered heat. Voyager fights this not with action, but with sheer, stubborn material integrity. Its aluminum structure, its beryllium-copper antenna, its gold-plated records. These materials don't oxidize, don't decay in the vacuum. They are subject only to the sublimely slow processes of cosmic ray sputtering, where individual atoms might be knocked off over millions of years, and the even slower creep of metallic fatigue at temperatures near absolute zero. In human terms, it is immortal. It will remain recognizable as a crafted object for timescales that dwarf human history. This brings us to a profound and unsettling thought. Voyager 1's journey is a mirror that reflects the transient nature of its creators. We are building a legacy that will outlast us by orders of magnitude. The pyramids are a few thousand years old. The oldest human artifacts are stone tools a few million years old. Voyager and its twin Voyager 2 will be intact, identifiable artifacts tens of millions, even hundreds of millions of years into the future. They will be drifting through space long after every trace of the civilization that built them has been scoured from the surface of Earth by wind, ice, and geologic upheaval. In a very real sense, these two probes will become the final and longest-lasting monuments to the human species. The Golden Record is not merely a greeting card. It is our civilization's last will and testament, filed with the cosmos. What, then, does it mean to travel through the Oort cloud, this unimaginably vast and lonely realm that will be Voyager's home for 30,000 years? This is not a dense field of ice blocks. It is a sphere of profound emptiness, sparsely populated by frozen primordial bodies in slow, vast orbits. Voyager will traverse this region like a single dust mote drifting through an empty cathedral. The chances of it coming close enough to any Oort cloud object to be seen, let alone impacted, are infinitesimally small. Its passage will be utterly dark and silent. The sun will have shrunk to a point of light barely brighter than other stars, a faint reminder of a gravitational tether that still weakly holds. For 30 millennia, the probe will be a prisoner of the sun's gravity, albeit in its most distant, feeble dungeon. Its escape will be so slow as to be imperceptible. Once free, it enters the true interstellar medium. The data it has sent back in recent years has already revolutionized our understanding of this region. It is not a uniform, placid sea. Voyager discovered that the boundary of our solar bubble, the heliopause, is foamy with magnetic bubbles, a turbulent zone where the sun's magnetic field lines break and reconnect. The interstellar medium itself is a patchwork of clouds. Voyager is currently in what is called the local interstellar cloud, a region of slightly denser hydrogen and helium. In about 2,000 years, it will likely enter the next cloud, the G cloud, home to the Alpha Centauri system. These clouds are like different currents in a galactic ocean, each with its own density and temperature. Voyager will sample them all, silently, its instruments long dead, becoming a physical probe moving through environments we can currently only study from afar. Its trajectory is not a straight line out of the galaxy. The Milky Way is a rotating disk, and Voyager is caught in its dynamics. While it speeds away from the Sun at 17 kilometers per second, the Sun itself is orbiting the galactic center at about 220 kilometers per second. From a galactic perspective, Voyager's path is a complex, slowly evolving spiral. It orbits the galactic center just as the Sun does, but on a slightly different path with a slightly different tilt. It will oscillate above and below the galactic plane, completing a galactic orbit roughly every 225 million years, but never in perfect sync with its stellar siblings. It is a lone wanderer on a galactic pilgrimage, its route a testament to the initial velocity imparted by a Titan III rocket and the gravity of Jupiter. The stellar encounters we can predict, Gliese 445 Sirius, are mere flashes in this billion-year journey. They are not destinations, but temporal landmarks in a voyage without a map. In the immense spans between these landmarks, the galaxy will transform. Stars Voyager once knew will die. New constellations will form from stellar nurseries it will never see. And through it all, the silent, dark probe persists, a piece of 20th century technology fossilized in the 21st, destined to become an anachronism of unfathomable age. Could it ever be found? The Golden Record was crafted with that hope. however faint. The probability is so low as to be effectively zero, but not quite zero. In a galaxy of hundreds of billions of stars, over quintillions of years, even the most unlikely events may occur once. If some unimaginably advanced spacefaring civilization were to ever stumble upon it, perhaps swept up by a vast interstellar harvesting operation or detected by a sensitive survey of anomalous non-natural objects, what would they make of it? They would be archaeologists of the cosmos, uncovering a relic from a long-vanished species on a world that no longer exists. The golden cover with its engraved instructions, the record itself with its sounds of Earth, the images of human beings, all of it would be a puzzle box from the deep past. It would tell them not just about us, but about our yearning to be known, our desire to shout our existence into the void. In that potential far-fetched moment of discovery, Voyager's ultimate purpose would be fulfilled, to testify that we were here, that we wondered, and that we tried to reach out. But the more likely, and in some ways more poetic, fate is that it will never be found. It will simply travel on, a permanent addition to the galaxy's background population of inert matter. It will become a piece of galactic driftwood, a tiny, artificial planetesimal orbiting the heart of the Milky Way until the end of stars. This, perhaps, is the most honest answer to how far can it travel. It will travel until the universe itself changes shape in ways we can barely model. Current cosmology suggests a future of expanding emptiness, the heat death, where all energy is evenly distributed and no work can be done. In such a universe, Voyager would still exist as a configuration of atoms, drifting in perfect darkness and perfect cold. Its journey would have no witness, not even itself. It would simply be, a monument without an audience, a story without a reader. Its travel would be absolute, pure, and eternal motion in a static, infinite canvas. So, when we ask, how far can the Voyager 1 travel? We are asking a question about infinity. We are asking about the legacy of a curious species inscribed on a metal disc and flung into the dark. We are asking about the endurance of memory in a universe that seems built on forgetting. The probe's distance from Earth is a number that updates daily, growing larger. But its true distance is measured in the future it has yet to traverse, a future that stretches beyond the life of our sun, beyond the glow of our galaxy, into the cooling embers of the cosmos itself. Voyager 1 is humanity's first step into eternity. It is our message in a bottle, our time capsule, our tombstone, and our ambassador. Its journey is finite only in the sense that the matter composing it will one day, after eons upon eons, succumb to proton decay or a random quantum event. But in any time scale that holds meaning for life, for consciousness, for civilization, it is endless. It will travel as far as time allows, carrying a whisper of the pale blue dot into the everlasting night. This galactic orbit it shares with our sun, yet undertakes alone, introduces another fascinating dimension to its travel: precession. Just as a spinning top wobbles on its axis, Voyager's orbital path around the galactic center will slowly rotate. Over hundreds of millions of years, its elongated track will twist, tracing a complex rosette pattern in the vast disk of the Milky Way. It will never retrace its own steps. Its journey is a unique, non-repeating path through the galaxy's star fields, a single, infinite line drawn in the ledger of cosmic motion. And what of the environment through which it will drift for these eons? The interstellar medium is not perfectly empty. It contains fine dust grains, perhaps no larger than a virus. Over tens of millions of years, these microscopic particles will have a sand-blasting effect, a process called sputtering. Atom by atom, the surface of Voyager's aluminum skin and its golden record cover will be eroded. The erosion rate is minuscule, perhaps a millimeter every few 100 million years. But given enough time, even this gentle, persistent rain will wear down its features. The engraved instructions on the record cover may become faint, then illegible. The spacecraft's shape will soften, its sharp edges rounded by cosmic sandpaper. Yet its core mass, its essential structure, will remain intact for far longer. It is a lesson in geological timescales applied to a human artifact. It will weather the galaxy, not in centuries, but in galactic years. This leads to a staggering consideration, the possibility of stellar close encounters that are not gentle passes. The galaxy, for all its emptiness, is dynamic. Stars are born in clusters and can be ejected, becoming hypervelocity stars racing through the Milky Way. While rare, a close gravitational interaction with a passing star, or more likely, a rogue brown dwarf or stellar mass black hole, could significantly alter Voyager's course. It could be flung onto a faster trajectory out of the galaxy entirely, becoming a true intergalactic traveler. Conversely, a close gravitational encounter could send it plunging on a more radial orbit toward the crowded galactic bulge. The probabilities of such dramatic events are vanishingly small over a few billion years. But as the timeline stretches toward 1 trillion, they become non-zero. Voyager's path, so precisely calculated for its first century, becomes subject to the whims of celestial chaos over the deep future. Its trajectory is only certain in the short term. In the long term, it is a statistic, a subject of gravitational probability. Within this incomprehensible time span, even the golden record's medium faces a silent adversary. The copper disk, plated with gold and encased in its protective aluminum jacket, is susceptible to the internal effects of radiation. The constant bombardment by cosmic rays over millions of years can induce gradual changes in the crystalline structure of the materials, potentially degrading the analog information stored in the record's grooves. The images and sounds we so carefully inscribed are, in the longest view, temporary. They may last hundreds of millions, even billions of years, a duration that dwarfs all of human history. But they are not infinitely durable. The message may fade before it is ever found, leaving only a strange, sculpted artifact of unknown purpose. This imbues the record with a poignant duality. It is both an attempt at eternal communication and a testament to the inevitable entropy that claims all ordered things, even in the vacuum of space. Yet, long after the grooves have become unreadable, the artifact itself will speak volumes. Its geometry is undeniably artificial. The hexagonal bus, the conical RTG housing, the large parabolic dish, these are shapes not found in nature. Any future finder, even one with no concept of human technology, would recognize it as a constructed object. It would be a mystery, a fossil of intelligence. In this way, Voyager's very form is a more universal message than the specific contents of the record. It says, simply, a maker existed. As we contemplate these deep futures, we must also confront the limits of our own models. Our predictions of Voyager's path for the next few million years are robust, based on well-mapped stellar positions and velocities. But beyond that, the uncertainty grows. The Milky Way will merge with the Andromeda Galaxy, beginning in about 4 billion years. This process, taking hundreds of millions of years, will gravitationally stir the stellar population. While direct stellar collisions are unlikely, the tidal forces and changing gravitational potentials will scatter stars and Voyager with them onto new, unpredictable orbits. Our probe will be a witness to this cosmic event.
In 1977, humanity embarked on one of its most audacious ventures, launching the Voyager spacecraft into the vastness of space. These twin probes, symbols of our insatiable curiosity, ventured far beyond the familiar planets, aiming to uncover the mysteries of the very edges of our solar system. As we journey with the Voyagers, we bear witness to their incredible odyssey, exploring realms where no probe has ventured before. Their golden records, a testament to the human spirit, carry our greetings to any who might find them in the cosmic ocean. Yet our exploration does not end with the Voyagers. Far beyond the gas giants, in the shadowy fringes of our solar neighborhood, lies Pluto. This distant world, once a planet in our textbooks, now stands as a gateway to the outer solar system. Through the eyes of New Horizons, we have glimpsed its wonders, towering ice mountains, vast nitrogen glaciers, and the enigmatic heart-shaped Tombaugh Regio. Pluto, in its silent beauty, challenges our understanding and invites us to delve deeper into the unknown. Beyond Pluto, whispers of an unseen world stir the scientific community. This elusive Planet 9, hidden in the darkness, bends the paths of distant objects with its gravitational embrace. Its existence, inferred from the strange orbits of trans-Neptunian objects, hints at a world yet to be seen, a planet at the very boundaries of our solar system. Join us on a journey to the mysteries on the boundaries of the solar system, where the Voyager saga, the enigmatic Pluto, and the elusive Planet 9 await. In the sweltering summer of 1977, a cosmic opportunity loomed on the horizon. The planets of our solar system were aligning in a way that happens only once every 176 years. This rare celestial event opened the way to the unknown and gave us a chance to embark on a grand journey to the outer planets. Using this happy coincidence, NASA engineers and scientists conceived of a mission in which two probes would slingshot from planet to planet, using the gravitational pull of each to propel them farther into the depths of space. The technological marvels that were Voyager 1 and Voyager 2 were equipped with the most advanced instruments of their time. From imaging systems capable of capturing Jupiter's swirling storms to magnetometers designed to study Saturn's magnetic fields, these spacecrafts were to rewrite our understanding of the solar system. But the journey to the launch pad was fraught with challenges, budgetary constraints, technological hurdles, and the boldness of the mission objectives pushed the team to the limit. Every component of the spacecraft had to be painstakingly tested, every system optimized for the rigors of space. As the launch dates approached, the excitement was palpable.
3, 2, 1. MDS, we have ignition, we have a liftoff.
Soaring into the skies, these twin messengers carried with them the hopes and dreams of all mankind, embarking on a journey that would forever change the way we think about the cosmos. When Voyager 1 and Voyager 2 traveled beyond the asteroid belt, they were greeted by the colossal presence of Jupiter, the gas giant that gravitationally dominates our solar system. These encounters set in motion a series of groundbreaking discoveries that would overturn our view of the outer planets. Armed with a host of sophisticated instruments, the probes peered into the planet's turbulent atmosphere, revealing the dynamic and violent nature of its storms. The Imaging Science System, a key component of Voyager's arsenal, captured stunning details of the Big Red Spot, a storm larger than Earth itself, and revealed never-before-seen features. But perhaps one of the most unexpected discoveries was the existence of Jupiter's thin ring system, a ghostly band of dust and particles girdling the planet. This discovery, made possible by the ship's photopolarimeter, disproved the notion the rings were a feature exclusive to Saturn. Among Jupiter's moons, Io stood out for its fiery temperament. The observations revealed a world with volcanic activity, the first time such phenomena have been observed outside of Earth. Moreover, Io is the most volcanically active body in our system, its surface forever changing under the inexorable forces of its interior. Images of towering plumes and lava flows have changed our understanding of geologic processes in the solar system. As the Voyagers continued their journey to Saturn, unprecedented beauty awaited them. The complex and intricate structure of Saturn's rings came into view, and the probe's cameras capture the subtle interplay of light and shadow among the countless ice particles. The scientific instruments aboard the spacecraft, especially the radio system, played a crucial role in studying the composition and dynamics of Saturn's rings. The data collected revealed the complex structure of the rings, including the mysterious gaps and braids phenomena whose formation continues to intrigue scientists to this day. Titan, Saturn's largest moon, was another highlight of the mission. Shrouded in a thick atmosphere, Titan was a world of mystery, its surface hidden from view. However, thanks to the ingenuity of Voyager's instruments, glimpses of this mysterious moon suggested the presence of liquid hydrocarbon lakes and a complex weather system, sparking curiosity and speculation about the possibility of life on it. The Voyager 1 and Voyager 2 encounters with Jupiter and Saturn have not only expanded our knowledge of the hot gas giants, but have also opened new frontiers in the exploration of the outer solar system. In the cold and distant reaches of our solar system, Voyager 2 set out for a solitary encounter with Uranus, the enigmatic ice giant. This historic encounter in January 1986 offered a glimpse of a world that had previously been just a pale blue dot in Earth-based telescopes. Uranus has presented an enigma to scientists with its peculiar tilted axis lying almost parallel to the plane of the solar system. This unusual orientation, with poles that alternately bask in the sun and languish in decades of darkness, has a profound effect on the planet's weather and atmospheric dynamics. As Voyager 2 approached, its instruments, including the narrow-angle Imaging Science System camera, began to capture unprecedented images of Uranus's atmosphere and its suite of moons and rings. The pale blue color of Uranus hid the complex structure of the atmosphere. Faint bands of clouds and previously invisible rings girdling the planet. One of the most striking discoveries was the nature of Uranus's magnetic field, revealed by the spacecraft's magnetometers. Unlike the Earth, whose magnetic axis coincides exactly with the axis of rotation, Uranus's magnetic field was found to be significantly displaced and tilted, suggesting a complex and possibly multi-layered internal structure. Leaving Uranus behind, Voyager 2 continued its journey to Neptune, the most distant of the known planets. In August 1989, mankind saw Neptune for the first time up close. A dynamic and turbulent world, at the center of which was the Great Dark Spot, a storm the size of the Earth. Neptune's atmosphere, buffeted by supersonic winds, paints a portrait of a planet alive with weather disasters. The spacecraft and its suite of instruments have delved into the mysteries of these winds, capturing the movement of cloud formations and the complex pattern of Neptune's faint rings. Among Neptune's moons, Triton stands out for its retrograde orbit and geologically young surface. Voyager 2 images of Triton showed a frozen landscape dotted with geysers spewing nitrogen gas and dust into space, hinting at a geologically active interior. Voyager 2's encounter with Uranus and Neptune have expanded the frontiers of our knowledge, revealing the diversity and dynamism of the outer planets. These fleeting visits have provided a treasure trove of data that continues to influence our understanding of the icy giants of the solar system. Moving farther and farther away, with limited resources, mission controllers face the difficult question of which instruments should be left operational. To extend the life of the mission, non-essential systems, including the camera, were planned to be shut down permanently. But in a moment that epitomized the human spirit of exploration and reflection, astronomer Carl Sagan proposed a bold idea. Before the camera goes silent forever, he suggested that Voyager 1 take one last picture of Earth, a farewell shot of our home planet from the edge of the solar system. On February 13, 1990, the spacecraft warmed up its cameras for 3 hours. The spacecraft's science platform then took a series of images from a distance of about 4 billion miles that would later be combined into a mosaic of the solar system. Among the myriad scientific achievements, it was Voyager 1's gaze toward its home planet that captured the collective imagination of humankind. That pale blue dot is a testament to our insignificance in the vast expanse of space and a poignant reminder of our shared responsibility to preserve and protect the only home we have ever known. In an odyssey that stretches beyond the bounds of human perception, Voyager 1 and Voyager 2 traveled beyond the confines of our solar system, traversing the vast, uncharted territories of interstellar space. This monumental passage marked the first time humanity had traveled beyond the heliopause, the boundary where the sun's influence wanes and the mysteries of the cosmos are fully revealed. The heliopause is the extreme boundary of the solar zone, or domain, where the solar wind, a stream of charged particles emanating from the sun, meets the interstellar medium, the matter that fills the space between the stars in our galaxy. At this boundary, the external pressure of the solar wind is balanced by the internal pressure of interstellar gas and magnetic fields, creating a turbulent region that marks the end of the sun's influence. When Voyager 1 approached this boundary in August 2012, it became the first man-made object to cross interstellar space, providing scientists with direct measurement of the boundary for the first time. At that point, the instruments aboard the spacecraft, though developed in the 1970s, continued to transmit invaluable data back to Earth, recording a sudden decrease in solar wind particles and a corresponding increase in high-energy cosmic rays from outside our solar system, increasingly revealing the history of our universe. Voyager's journey beyond our solar system has not only expanded our understanding of the universe, but it's also paved the way for future endeavors in the never-ending quest to explore space. Their legacy is captured in the vast amount of data about the outer planets, their moons, and the heliosphere, and continues to be a cornerstone for scientific research, influencing the study of fields ranging from planetology to astrophysics. These missions have provided insights into the dynamics of planetary atmospheres, the structure of rings, and the nature of magnetic fields, setting the stage for subsequent missions. In the spirit of Voyager's pioneering voyage, subsequent missions have been designed to delve deeper into the mysteries uncovered by the twin spacecraft. For example, the Cassini-Huygens mission expanded our knowledge of Saturn by deeply analyzing the planet's rings, moons, and atmosphere. Similarly, the Juno mission looked beneath Jupiter's clouds, revealing the secrets of its internal structure and magnetic field. Looking to the future, the scientific community is clamoring for dedicated missions to Uranus and Neptune. These proposed missions are aimed at a comprehensive study of the icy giants, exploring their unique atmospheres, complex ring systems, and diverse moons. Such studies will not only improve our understanding of these enigmatic planets, but will also shed light on the formation and evolution of the solar system. Among the myriad scientific instruments and revolutionary technologies aboard the Voyager spacecraft is a message not for us, but for the unknown, for the future, or perhaps for other space dwellers. That message is the Golden Record, a 12-inch gold-plated copper disc on which are recorded sounds, images, music, and greetings from Earth. The Gold Record serves as a time capsule, a snapshot of humanity and our planet at the end of the 20th century. Its contents have been carefully selected to show the diversity of life and culture on Earth, from the sounds of nature, such as birdsong and the sound of the ocean, to music from different cultures and eras, including Bach, Beethoven, and traditional music from around the world. Decisions about the content of the Golden Record were guided by the desire to present a comprehensive picture of Earth and humanity. The team, led by Carl Sagan, put a lot of thought into including content that would not only convey the complexity and beauty of life on Earth, but also reveal fundamental scientific concepts, such as the structure of DNA and the location of our planet in the solar system. The cover of the Golden Record is decorated with symbolic instructions, the universal language of science and mathematics, designed to tell potential aliens how to decipher the disk. These symbols explain the origins of the record and provide instructions on how to play the audio content, ensuring that the message is understood throughout the space, transcending language and cultural barriers. The record is a testament to humanity's hope and desire for contact, communication, and connection, not only with our future generations, but perhaps with other beings who will one day find this bottle tossed into the cosmic ocean, carrying a message of a small, distant world full of life and dreams. As Voyager 1 and Voyager 2 continue their silent odyssey into the depths of interstellar space, the task of keeping in touch with these distant explorers is becoming increasingly difficult. Billions of miles from Earth, the faint signals transmitted by the spacecraft take more than 22 hours to cross the cosmic expanse and come like whispers from the void. The Deep Space Network, an array of giant radio antennas scattered around the globe, serves as the ears of the Earth, listening intently to the faint signals of spacecraft. As the spacecraft travel farther into space, the ingenuity and foresight of the engineers who designed and built these probes becomes increasingly evident. The longevity and success of the missions can be attributed to an amazing feat of engineering. Designed to last only 5 years, the spacecraft have exceeded their expected lifespan many times over, thanks to redundant systems, robust construction, and the use of radioisotope thermoelectric generators, or RTGs, for power generation. These RTGs convert the heat generated by the decay of plutonium-238 into electricity that fuels the spacecraft's instruments and communication systems. As RTG power decreases, mission controllers are faced with making difficult decisions about which instruments should continue to operate. This careful management of dwindling resources ensures that the most important science instruments remain operational for as long as possible, continuing to collect invaluable data at the frontiers of space. Looking ahead, we expect the Voyagers to continue their silent journey long after their last instruments have fallen silent. Driven by the momentum of their initial launch and gravitational support, they'll drift as emissaries of Earth, perhaps for billions of years. The idea that these spacecraft may one day be the only remaining evidence of humanity's existence, taking the golden records into the cosmic ocean, has its poetic note. The final frontier for Voyager is marked not by a physical boundary, but by our ability to communicate across vast cosmic distances. But even as spacecraft fade into silence, their legacy lives on, a testament to human curiosity and the unquenchable desire to explore the unknown. In the shadowy depths of our solar system, far beyond the last known gas giant, lies a world shrouded in intrigue and mystery. This is Pluto. Once considered the ninth planet, it now occupies a separate category, at the center of heated debate and scientific curiosity. For decades, Pluto remained a blurry speck of light in our most powerful telescopes, a distant dot at the edge of our vision. It was a world waiting to be discovered, keeping its secrets in the cold, dark depths of space. At the dawn of the 21st century, an unprecedentedly ambitious mission began. The New Horizons spacecraft embarked on a billion-mile journey to explore Pluto's icy frontiers. What it discovered was astonishing in its diversity: towering ice mountains, huge nitrogen glaciers, and the legendary heart-shaped Tombaugh ratio, an object so large it can be seen from space. But these discoveries are just the beginning. Join us as we journey together into the icy depths of the outer solar system, where one dwarf planet is eagerly waiting to tell us its story. In the early 20th century, the search for a ninth planet, the mysterious Planet X, gripped the world of astronomy. The search was not just about adding another name to the list of planets. It was about understanding the unseen forces that shape the orbits of the then already known celestial bodies around us. At the center of this search was Lowell Observatory in Flagstaff, Arizona, where a young astronomer named Clyde Tombaugh embarked on a painstaking journey through space. Armed with a telescope and photographic plates, Tombaugh set out to scrutinize the night sky, inch by inch, in search of an elusive planet that eluded detection. On a February night in 1930, Tombaugh's diligence paid off. Among the countless stars, he spotted a moving object, a tiny speck of light that was unlike anything else he had observed. It was Pluto, a distant world named after the Roman god of the underworld, a discovery that would change the boundaries of our solar system. As the decades passed, Hubble's Space Telescope brought us closer to Pluto than ever before. Launched into orbit in 1990, Hubble's powerful lens pierced the veil of distance separating us from the outer solar system. The first images of Pluto were a revelation, transforming the distant dwarf planet from a mere glowing dot to a world with distinct features. These Hubble images provided the basis for a more detailed study. They showed Pluto's complex surface, marked by variations in brightness and color, hinting at a dynamic world waiting to be explored. An odyssey of discovery that began with a single blinking dot on a photographic plate has brought us to the threshold of a new frontier. Pluto, once a mere curiosity at the edge of our solar system, was about to reveal its secrets through a relentless pursuit of knowledge and a relentless spirit of exploration.
5, 4, 3, 2, 1. We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond.
In January 2006, humanity embarked on another of its most ambitious journeys. New Horizons, a spacecraft no bigger than a grand piano, was poised to cross the vast emptiness of space, heading for a world barely seen by human eyes. Its mission is to unlock the secrets of Pluto, a mysterious dwarf planet at the edge of our solar system. When New Horizons soared into the sky, it carried the aspirations of countless people who had devoted years to that moment. The journey was a marathon of cosmic proportions, spanning nearly a decade and more than 3 billion miles. With precision, it plotted a path through the void, guided by the gravitational slingshots of celestial bodies in its path. In 2015, after 9 long years, as New Horizons approached its distant destination, the whole world watched with bated breath. The first images were simply revolutionary. Pluto, which was once just a speck of light even in the most powerful telescopes, now appeared to be a world of mountains, valleys, and plains. The landscape that came into view was strikingly varied. Ice mountains, some as tall as the Rockies, rose proudly to the surface, their peaks shrouded in a blanket of methane snow. Sputnik Pallidie, a nitrogen ice plain, stretched across the entire dwarf planet, its surface mottled with a complex pattern of ridges and depressions. Among the most striking discoveries are signs of geological activity. Pluto, long thought to be a frozen relic from the dawn of the solar system, turned out to be alive. Glaciers of nitrogen ice slowly flowed across the landscape, and hints of cryovolcanoes indicated that this distant world was not as inactive as previously thought. New horizons leap into the unknown, bridge the gap between assumptions and reality. Pluto was no longer just a point of light in our telescopes. It was a dynamic world full of surprises and beauty, waiting at the edge of our solar system. It was just the beginning of a new chapter in our understanding of the cosmos. Pluto's expanse of rugged landscapes is home to one of its most mesmerizing features, the Sputnik Planitia. This enormous heart-shaped glacier is not just a striking visual landmark. It's a geological marvel that's changed the way we think about this distant world. The origin of Sputnik Pallidie is a story of cosmic forces. This vast basin, stretching more than 650 miles, is believed to have been formed by the impact of a massive celestial body, an event that changed Pluto's surface and possibly its entire geology. The basin was filled with various ices, mostly nitrogen, creating a smooth, reflective plain that contrasts sharply with the surrounding topography. The surface of Sputnik Planitia is modeled with a complex pattern of convection cells, each the size of a country on Earth. These cells are the surface manifestation of ice in slow motion, churning and flowing in response to the weak heat coming from Pluto's interior. This lava lamp-like process shows that Pluto is far from the inert, frozen world we once imagined. More mysteries lie beneath the icy facade of Sputnik Planitia. The uniform mass distribution in this region, obtained from spacecraft measurements, hints at the presence of a denser layer beneath the ice. Scientists speculate that this may be a subsurface ocean. It's possible that this reservoir could contain liquid water isolated by the ice crust above. Among other discoveries, scientists have also found that Pluto has an atmosphere hovering above its icy surface, as thin and fragile as an atmosphere can be on the cold fringes of the solar system. Composed mostly of nitrogen, with traces of methane and carbon monoxide, this thin veil provides clues to understanding the planet's most mysterious processes. The structure of the planet's atmosphere does not match the primary expectations. When New Horizons flew by, it found an atmosphere extending hundreds of miles above the surface, much more extensive than expected. This thin atmospheric layer is stratified and has a complex interplay of gases that scatter and refract sunlight, creating a mesmerizing blue hue that resembles Earth's own sky. Because Pluto's journey around the Sun is unlike any other planet in our solar system, with an orbital period of an unimaginable 248 Earth years, each season on Pluto can last decades. Its trajectory is markedly elliptical. It is much closer to the Sun at perihelion than at aphelion, and its axis is tilted at an angle of 120 degrees, resulting in extreme seasonal variations on its surface. As Pluto approaches its perihelion, the heat from the distant Sun, though faint, is enough to cause a remarkable transformation. Surface ices, composed of nitrogen, methane, and carbon monoxide, begin to sublimate, a process by which these ice change from a solid state to a gaseous state, without changing to an intermediate liquid state. This sublimation is most pronounced in regions exposed to the Sun's weak but constant rays, resulting in an increase in atmospheric pressure as gases previously trapped in ice form are released to the outside. This outgassing thickens Pluto's atmosphere, making it more substantial during these warm periods. The atmosphere expands, rising hundreds of kilometers above the surface, much more than during colder periods. This expansion is uneven, and it's influenced by Pluto's topography and the composition of its ice, creating a complex and dynamic atmospheric system. As Pluto continues its long journey, moving away from the Sun and toward more distant parts of its orbit, the atmosphere is undergoing a dramatic turn of events. The gases that once thickened the atmosphere are now cooling and condensing, falling back to the surface as a fine snow of nitrogen, methane, and carbon monoxide. This cyclical process of sublimation and condensation is a defining feature of Pluto's climate, changing its surface over the centuries. This dance of ice and vapor unfolding over the course of Pluto's long year paints a portrait of a world in constant motion. Far from a static, frozen wasteland, Pluto's surface is a dynamic environment, a reminder of the active and ever-changing nature of even the most distant members of our solar system. Another exciting discovery about Pluto's atmosphere is its escape rate. Unlike the strong magnetic fields and gravitational pull that protect the atmosphere of the larger planets, Pluto's weak gravity allows much of its atmosphere to escape into space. This atmospheric escape contributes to the ionized gas tail, an invisible comet-like trail that Pluto leaves behind it as it orbits the Sun. This leakage is not a steady, gentle flow, but a complex interaction with a solar wind, a stream of charged particles emanating from the Sun. These particles, colliding with escaping atmospheric gases, create a dynamic and ever-changing environment around Pluto, a miniature magnetosphere in which the drama of solar and planetary forces is played out. From Pluto's dynamic atmosphere and unique climate, we move to its largest moon, Charon, and discover relationships and landscapes that change the very definition of celestial bodies in the outer part of our solar system. Charon, Pluto's largest satellite, orbits in synchronized motion with it. Discovered in 1978, this celestial body turns out to be more than just a satellite. It is a whole world filled with geological wonders and a unique history that's intertwined with that of Pluto. As New Horizons flew past Charon, they saw a landscape of canyons so deep and wide they could easily swallow up parts of Earth's Grand Canyon. These chasms stretched across the surface of the satellite, telling a story of geologic upheaval. Mountains rising dramatically against the lunar surface reveal a dynamic history, their peaks casting long shadows over the valleys below. The origins of Charon's dramatic topography lie in its past, marked by internal processes and possibly cryovolcanic activity. As Charon cooled and compressed over millions of years, its crust split, resulting in vast canyons. At the same time, mountains may have formed from tectonic activity as the moon's surface flexed and broke, pushing some areas upward and raising peaks. The interaction between Pluto and Charon is a kind of gravitational ballet in which both bodies are locked in a synchronized orbit. This means that Charon always faces Pluto on the same side, and vice versa, a phenomenon known as tidal locking. Unlike most moons, which orbit around their planets, Pluto and Charon orbit around a point in the space between them, known as the barycenter. This unique arrangement challenges the conventional definitions of planets and moons, suggesting a binary system where both bodies are partners in their celestial tandem. This gravitational partnership extends beyond Pluto and Charon, affecting the orbits of Pluto's smaller moons, Styx, Nix, Kerberos, and Hydra. Charon's presence stabilizes these smaller satellites, maintaining the complex balance of the system. The dynamics of this mini-solar system give us valuable insight into the gravitational interactions that shape the orbits of celestial bodies throughout the universe. Located in the vast realm of the Kuiper Belt, Pluto stands like a sentinel at the edge of our solar system. This region, a vast cluster of icy bodies extending beyond the orbit of Neptune, is a relic of the early solar system and holds the keys to understanding the formation and evolution of our cosmic neighbor. Pluto, once thought to be the 9th planet, has found its relatives among the vast number of Kuiper Belt objects, or KBOS, like dwarf planets like Haumea and Makemake, to smaller, lesser-known bodies. Each KBO has its own story that contributes to the picture of the solar system. Pluto's varied landscape, from nitrogen ice plains to towering mountains and dynamic atmospheres, reflect the complexity and diversity of the Kuiper Belt landscape. The Kuiper Belt is a window to the past, a frozen archive of the birth of the solar system. The objects included in it, including Pluto, are remnants of the time of planetary formation, untouched by the sun's heat. Their composition, ice mixed with rocks, gives an idea of the materials that abounded in the early solar system and allows us to understand the processes that led to the birth of the planets. Exploring Pluto and its neighbors in the Kuiper Belt has far-reaching implications for our understanding of the solar system. Each mission, like the New Horizons flyby of Pluto and Arrokoth, peels away layers of mystery, revealing the conditions and processes that prevailed in the outer solar system billions of years ago, forcing us to consider the dynamics of planetary formation and the boundaries between planets and smaller celestial bodies. Pluto's position in the Kuiper Belt emphasizes the interconnectedness of celestial bodies, from the smallest piece of ice to the largest gas giant. The dynamics of the Kuiper Belt, with its resonances and orbital interactions, influence the stability and evolution of the outer solar system, shaping the trajectories of comets and affecting the environment of Neptune. However, New Horizons exploration didn't end there. After its historic flyby of Pluto, it traveled onward to Arrokoth, a Kuiper Belt object, meeting it on January 1, 2019, marking the next milestone in space exploration. Arrokoth, resembling a clay snowman, demonstrated the soft merger of two primordial objects, offering unprecedented insight into the building blocks of the early solar system. The story of Arrokoth's formation is a testament to the slow and gentle processes that dominated the outer regions of the early solar system. The large lobe, called Bennu, is not a single formation, but a cluster of a dozen rocks, each more than 3 miles wide, huddled around a central slab. This cluster refutes previous notions of high-velocity collisions in planetary formation, suggesting instead a gradual merger at speeds of less than a dozen feet per second. This intricate interaction between two lobes, losing angular momentum and smoothly merging, forms an image of a patient cosmos where the building blocks of the planets come together in a heavenly cycle of gravity and time. Looking ahead, the horizon of solar system exploration is littered with potential. Concepts for the next New Horizons missions are already stirring the imagination of scientists and engineers. One of them envisions an orbiter capable of mapping Pluto's surface with unprecedented resolution, penetrating the mysteries of its small satellites, and even exploring the eternal darkness of the regions enveloped by Pluto's axial tilt. The project, inspired by the legacy of Cassini, proposes to use Charon's gravity to create complex orbital trajectories around Pluto, allowing for a comprehensive study of the dwarf planet and its satellites. Such missions could utilize electric propulsion, replicating the success of NASA's Dawn, and could potentially go beyond the Pluto system and explore new frontiers in the Kuiper Belt. New technologies such as direct fusion drives promise to propel future spacecraft to the outer solar system with unprecedented speed and efficiency. A report titled "The Fusion-Enabled Pluto Orbiter and Lander" from NASA's Innovative Advanced Concepts (NIAC) program describes a mission to Pluto with a direct fusion drive. Using a fusion reactor, a 1,000-kilogram orbiter and landing module could reach Pluto in just 4 years, more than twice the speed of New Horizons. These promising propulsion systems could significantly shorten the travel time, opening new pages in the exploration of the distant worlds of our outskirts. As we travel the vastness of space, exploring distant worlds and discovering the secrets they hold, our understanding of the cosmos continues to evolve. The story of Pluto, from its discovery to the present day, is a vivid reminder of the dynamic nature of science and our attempts to categorize the universe around us. Pluto's unique orbital interaction with Neptune adds another layer to its fascinating story. During its 248-year orbit around the Sun, Pluto appears closer to the Sun than Neptune for a brief time, challenging the view of its position as the 9th planet. This crossing of orbits, when Pluto and Neptune change places, occurs because of the elliptical trajectory of Pluto's orbit and its inclination relative to the plane of the solar system. Despite this temporal shift, Pluto's overall trajectory ensures that there's no risk of collision with Neptune due to their mutual orbital resonance. The rather lengthy debate over Pluto's planetary status has long sparked discussion and controversy that reaches far beyond the astronomical community. In 2006, the International Astronomical Union revised the definition of planet in our solar system, which led to Pluto's reclassification as a dwarf planet. This moment was not only a turning point for Pluto, but also a catalyst for the reclassification of celestial bodies. Pluto's history is closely tied to the Kuiper Belt, a region teeming with objects that blur the boundaries between planets, moons, and smaller celestial bodies. Studying Pluto and its neighbors makes us think about the wide range of characteristics that celestial bodies can possess, from their atmospheres and geology to their orbits and interactions. In the grand canvas of the cosmos, every thread, from the smallest asteroid to the mightiest gas giant, plays a critical role in the history of our solar system. As we stand at the threshold of new exploration, Pluto's legacy and the knowledge gained from the Kuiper Belt serve as beacons guiding us to a deeper understanding of our place in the universe. Rethinking our cosmic neighborhood is not just about the labels we place on it, but about embracing the diversity and complexity of the universe. In the vast, silent expanse of our solar system, beyond the familiar brilliance of Neptune, rumors of some unseen presence have been stirring astronomers for quite a few years now. This mysterious force, unseen but undeniable, stretches the very fabric of our cosmic neighborhood, bending the paths of distant objects with its invisible grip. Here in the shadowy depths of space, where the warmth of the sun barely reaches, lies a mystery that's baffled the brightest minds. The hypothetical world known only as Planet 9, whose existence can be determined not by direct observation, but only by the subtle interaction of trans-Neptunian objects performing complex orbital motion. Could there be a rogue planet, shrouded in the darkness of space, exerting its influence from afar? A world that defies our understanding and challenges the very limits of what we know about our solar system. Join us as we piece together clues scattered in the back of the solar system in search of a planet that has so far eluded our sight. In the early 1990s, the outer reaches of our solar system began to reveal their secrets. Astronomers discovered a region teeming with icy bodies, now known as the Kuiper Belt. This discovery marked the beginning of a new chapter in our cosmic journey, expanding our understanding of the boundaries of the solar system. Among these distant wanderers was Pluto, long considered the ninth planet and proudly bearing that title since its discovery in 1930. But as the Kuiper Belt uncovered its treasures, Pluto's status began to be questioned. The discovery of objects such as Eris, that rivaled and even surpassed Pluto in size, sparked a debate that shook the foundations of planetary classification. In 2006, the International Astronomical Union was faced with an unresolved situation. What defines a planet? The answer to this question led to a controversial decision that downgraded Pluto to a dwarf planet. This decision, met with both approval and opposition, has swept through the astronomical community and the public, redefining the way we think about the solar system. In this cosmic controversy, however, the seeds of a new mystery were sown: the peculiar orbits of some Kuiper Belt objects, including the then distant newly discovered Sedna, hinted at an invisible influence from the shadows guiding these icy bodies. Could it be that another planet, hidden in the vastness of space, created the architecture of the outer solar system? This question ignited the imagination of astronomers like Mike Brown and Konstantin Batygin, who set out to find the truth. Their journey will lead them to speculate on the existence of Planet 9, a hypothetical world hiding behind Neptune, whose presence is signaled only by the interaction of the most distant members of the Kuiper Belt. a new planet emerging from the heart of controversy awaits discovery. As we move beyond the familiar boundaries of the inner solar system, a realm of icy bodies and distant orbits opens up before us. Here, in the cold, dark regions beyond Neptune, lies an enigma that has captivated astronomers for years. It's the Kuiper Belt, a vast ring of debris left over from the formation of the solar system. Among these celestial wanderers, a separate group shows peculiar behavior that contradicts the expected norms of orbital mechanics. These are detached TNOs, or trans-Neptunian objects, whose paths are free of Neptune's gravitational influence, and extreme trans-Neptunian objects, or ETNOs, whose orbits are so eccentric that they seem to be tethered to some invisible force. What could be the architect of this unusual behavior? The answer may lie in the gravitational anomalies that pervade this distant region. These anomalies, subtle but deep, indicate the presence of a massive object whose gravitational pull shapes the orbits of these distant objects. The detached TNOs, whose orbits seem to be unaffected by Neptune, hint at a disturbance in the gravitational harmony of the outer solar system. Meanwhile, ETNOs, with their extreme orbits, paint a picture of cosmic interaction guided by a hidden force. The quest to understand these gravitational mysteries led researchers to hypothesize the existence of Planet 9, a hypothetical world whose mass and orbit could explain these anomalies. By carefully mapping the orbits of these mysterious objects, scientists began piecing together the potential location and characteristics of this invisible planet. In the tranquil balance of our solar system, each planet plays its part, revolving around the sun in a centuries and centuries and centuries old rhythm. But beyond this familiar rhythm looms a shadowy figure, a silent participant whose presence is felt but not seen. Let's take a closer look at the Planet 9 hypothesis itself. In 2014, astronomers Chad Trujillo and Scott S. Shepard noted an intriguing similarity between the orbits of Sedna, 2012 VP113, and several other ETNOs, a phenomenon too unusual to be a mere coincidence. Trujillo and Shepard made a bold suggestion: the existence of an unknown planet whose orbit is a perfect circle between 200 and 300 astronomical units from the Sun. A few years later, in 2016, Mike Brown and Konstantin Batygin embarked on an intellectual journey delving into the mysteries of the outer solar system in order to develop this hypothesis. Through careful analysis and computational modeling, Brown and Batygin pieced together previously found gravitational anomalies that indicated the existence of a massive invisible planet. This hypothetical world, in their opinion, could be the key to unraveling the special dynamics of the outer part of the solar system. As their research progressed, so did their understanding of the potential characteristics of Planet 9. Its mass was originally thought to be 10 times that of Earth, but further research revealed that its mass was slightly less, but still significant, at about 5 or 6 Earth masses. This revision painted a picture of a planet powerful enough to control the orbits of distant objects, yet elusive enough to remain hidden from our most powerful telescopes. The influence of this hypothetical planet extends far beyond its immediate vicinity. Its gravitational influence can explain the clustering of the orbits of detached TNOs and the extreme trajectories of ETNOs, weaving together a complex picture of celestial mechanics. The hypothesis of Planet 9 sparked a flurry of scientific research, and astronomers around the world joined the hunt for this elusive neighbor. The search for Planet 9 is a journey fraught with difficulty, a testament to both the vastness of the universe and the limitations of our current technological capabilities. Its distant orbit, presumably huge and elliptical, leads it through the farthest reaches of our system. This region, where the light of the sun is almost unattainable, envelops the planet in total darkness. This remoteness poses a serious problem because the potential position of the planet can encompass vast portions of the sky, requiring extensive, focused searches covering these celestial expanses in painstaking detail. It's something akin to trying to find a needle in an astronomical haystack. Moreover, because of its distance from the Sun, the planet's surface temperature is extremely low, meaning it emits minimal thermal radiation, making infrared detection just as difficult. The lack of emitted and reflected light is compounded by the glare of distant stars and the myriad cosmic objects that fill the sky, each vying for the attention of our telescopes. Among other difficulties, the nature of the search is compounded by the planet's enormous orbital period, which is thought to be thousands of years. Because the planet's motion across the sky is imperceptibly slow from our earthly perspective. Even after a decade, Planet 9's position in space will have changed only slightly, making any attempt to observe its motion in the short term virtually impossible. This chilling rate of motion means that traditional methods of detecting planets by observing their transit or motion against the background of stars are not feasible. However, in their relentless pursuit, astronomers use an array of sophisticated techniques and instruments, from ground-based telescopes equipped with advanced adaptive optics to space-based observatories that circumvent the Earth's atmospheric distortions. So, in the pursuit of Planet 9, astronomers have had to go beyond traditional observational methods, leading to the development of several innovative approaches aimed at refining the elusive planet's location. They utilize unique aspects of the solar system's external environment and potential celestial interactions that Planet 9 may have with other objects. One of the proposed approaches has to do with potential moons that may orbit around Planet 9. Given its considerable mass, it is conceivable that it could have captured one or more moons during its long journey through the solar system. The concept is based on the process of tidal heating, a phenomenon in which the gravitational interaction between a planet and its moon causes internal heat to be released within the moon, potentially making it warmer than the parent planet. This is what allows the satellites Europa and Enceladus to have liquid subsurface oceans and also provokes vigorous volcanic activity on Io. This internal heating may cause the moons to emit infrared radiation more perceptively than Planet 9 itself, providing an indirect but promising avenue for detection. Another innovative method involves tracking the trajectories of interstellar asteroids passing through our solar system. These high-speed objects, coming from regions outside our solar system, could potentially be affected by the gravitational pull of Planet 9. By meticulously tracking the trajectories of such asteroids, astronomers can infer the presence and location of a planet from the subtle gravitational jolts it exerts on passing bodies. This method was demonstrated by studying the interstellar asteroid Oumuamua, whose path through our solar system may have been slightly altered by such a massive object. The trajectories of spacecraft passing through the outer solar system can also provide valuable insights. Like asteroids, when spacecraft travel vast distances between planets, their trajectories are slightly and subtly influenced by the gravitational forces they encounter. By analyzing the precise tracking data from these missions, scientists can detect unaccounted gravitational anomalies that may hint at the presence of Planet 9. This method requires accumulating huge amounts of data over long periods because the gravitational effects are incredibly subtle. However, the results can be very significant and will pay off the time spent. Moving from direct observation to indirect detection through a planet's influence on its environment may be the key to unlocking one of the greatest mysteries of our cosmic neighborhood. The search for Planet 9 has also spawned many theories and speculations about the true nature of this elusive object. Among the most intriguing are hypotheses that Planet 9 could be a primordial black hole or a dense dark matter clump, each representing a radical departure from the traditional planetary view. The idea that Planet 9 could be a primordial black hole introduces a sharp twist to the narrative. Unlike stellar black holes, formed by the collapse of massive stars, primordial black holes are theorized to have originated in a high-density environment shortly after the Big Bang. These hypothetical entities may be the size of an asteroid, but have the mass of a planet. The possibility that Planet 9 is one of these ancient, mysterious objects is compelling for several reasons. First, it would allow us to explain the gravitational effects attributed to it without the need for a visible planetary body. Secondly, this of course does not completely contradict the impossibility of its detection, since such an object would theoretically be no larger than a basketball. According to another theory, Planet 9 may be a concentrated blob of dark matter. This form of matter, which does not emit, absorb, or reflect light, accounts for a significant portion of the total mass of the universe, but remains one of the greatest mysteries. Dark matter clumps, theoretical clusters of dark matter, are thought to have arisen from density fluctuations in the early universe. As the universe expanded and cooled, these gravitational fluctuations led to the formation of dark matter structures ranging from small clumps to massive halos surrounding galaxies. If Planet 9 were a dense cluster of dark matter, it could exert the gravitational influence observed in the outer solar system without being directly observable using conventional telescopic techniques. The primordial black hole and dark matter clot hypotheses emphasize the profound implications of the search for Planet 9 far beyond the discovery of a new member of the solar system. Whether it's an ordinary planet, a primordial black hole, or a dark matter clot, one way or another we'll find ourselves on the favorable side of events. The search for Planet 9 is a testament to humanity's enduring curiosity and relentless pursuit of the unknown. A recent preprint of a research paper by the same Mike Brown and Konstantin Batygin and their colleague Matthew J. Holman entitled Pan-STARRS 1 Search for Planet 9, dated February 1, 2024, reflects the meticulous ongoing efforts to uncover this enigmatic member of our solar system. The study used extensive data from the Pan-STARRS 1 survey, which, with its deep and wide sky coverage, provided a unique vantage point for the search. By focusing on single night transients and using a sophisticated Keplerian orbit linking algorithm, the researchers sifted through billions of detected objects, a task akin to finding a single grain of sand among the entire North American coastline. This methodological approach represents a significant leap forward, building on the foundation laid by previous surveys, such as the Zwicky Transient Facility and the Dark Energy Survey. Despite the depth and breadth of the PS1 survey, the elusive ninth planet remained out of sight. No features matching the search parameters were found in the data. This result, while not leading to the discovery of a ninth planet, nevertheless narrowed the search area considerably, excluding 78% of the parameter space in which the planet could potentially reside. The remaining 22%, areas with poor observational coverage or inaccessible to current detection capabilities, represent the next frontier in this space search. The journey doesn't end with the PS1 research. The upcoming launch of the Vera C. Rubin Observatory promises to usher in a new era of astronomical observation with capabilities that can finally pierce the veil of mystery, including that which surrounds Planet 9. As we stand on the threshold of these future explorations, the search for Planet 9 remains a beacon of scientific inquiry, a reminder of the vastness of the universe and the small but significant place we occupy in it.